We will now start the next AGI lecture, which this time is about communication and socialization of AGI systems.
Okay, by this time we have basically very briefly introduced all the major components of the NARS system. Today, let's try to put things together. So we will start with the architecture of one implementation of the system. This one, you can see that we can compare it with the architecture I introduced several weeks before. You can see the basic idea remains the same. Okay. We still have a memory, we still have an inference engine, and there is a basic working cycle. You get input, put into buffer, which will be selectively put into the memory. And we select something from memory, feed it into the inference engine, and get result, which go back into a buffer, then it become some kind of cycle, and some result is selectively reported to the user. So you'll see the big picture remain the same. The major difference actually is this buffer. Okay. Or we can also say this buffer as well as what we call channel. Okay. So this part is basically the same. Of course, and previously we are talking about only an implementation of the bottom level or the basic level of now. Now we are talking about the full implementation. Okay. So the inference engine, clearly the content are different, and also the memory become more complicated, which we will mention later. So what is new here? You can see, roughly speaking, there are two major changes. Previously, we are talking about a single input-output channel, which basically communicate with the user who is also the manager, the controller, whoever you call it, who provide all the information to the system using NARSys. That's the formal language we use. And now you'll see that we allow a whole bunch of what we call channels. And at least the three of them, actually there are three different types, and for each type, there can be multiple channels. Okay. So each channel basically handles the communication between the system and one user or device or environment, whatever you call it, okay, which we are going to go through one by one. And previously, there's basically only one input-output channel. Now we have an unlimited number of them and also of different type. So this is one change. Another major change is previously we only have one buffer. And also the function of the previous buffer is pretty straightforward. It just serves as some kind of filter. You see, because of the assumption of insufficient knowledge and resource, the system cannot and will not try to handle all input and derive the conclusions. Instead, it will selectively process some of them. So this one will serve as that kind of filter. We talk about this priority value ranking, right? So that's the mechanism used to selectively working on the things that the system considers to be important and ignore the others, simply because it doesn't have the time to do all of them. And that function is still there. It's just now you'll see that we actually have a whole bunch of buffers. And this is what we call overall experience buffer, which basically serve the same role as this one. But instead, we dedicate some of the function to a few other buffers. This one, you can see that's what we call internal experience buffer, which just directly hold the direct result from the inference engine. Okay. And also not shown in this picture, but implied, there is a buffer, at least one, within each input-output channel. Okay. So everything when you put into the system, it will be put into a buffer within that channel first. which still serve the same basic functionality as some kind of filter. Okay, so you don't feed everything into the system. So you have kind of like a first line of filters in the channels, which each of them is for one type of thing. And the information there will be selectively fed into this overall experience buffer, which will do the second level selecting. Okay, so this will be this is a mechanism to handle more complicated input situations. Especially, you see that here we add in sensory motor channel, which will connect the system directly to the outside world through some sensors and actuators. For example, if you have a vision channel, and then you have visual information continuously, consistently fed into the system. Okay, clearly, that's a huge amount of information. What the system does is selectively pass some of them to the next level, and here do the same thing and pass some of them into memory. So what actually gets into the memory is typically a very small percent of the stuff you have in the channel. Okay. So that's another difference, that is the buffer. So basically the new change is the channels and the buffers. And the buffer also, now we add additional functionality compared to the previous one. Previously, all the inference happened in the inference engine using the material selected from the memory. Okay. And now we actually have two different places for reasoning, and still the majority of the work, the heavy duty part, is still in memory. But in each buffer, including everything in the channels and this one, we begin to do some pre-processing. So besides selectively take some things out of it, in the buffer, we also begin to do some type of reasoning. What kind of reasoning? Basically, there are two major types. One is to build some simple, relatively simple compound term. Based on what, especially a good example is the sensory motor channel. Okay, so that intuitively speaking, a sensory motor channel gave the system a stream of input signals, one after another, with a temporal order. Right, that flow into the system, no matter we're talking about visual or audio or any other things. So what the buffer does, not only select some of them, and also try to combine them into larger chunks. So instead of signal by signal, it will try to organize some signal into a larger unit. Say, for example, you have three signals kind of like always come together, and this three will be perceived as one single unit. That's a clearly efficient way to comprise the amount of information. Another thing related to it is the system will try to figure out or try to discover some relatively simple patterns. For example, A is always followed by B in a certain channel, so that in the future, whenever see A, the system is going to form an anticipation for B. Okay, and this is something we kind of like already mentioned before when you try to learn a temporal regularity. You start with a simple correlation, and then you use anticipation to collect your evidence, especially negative evidence. Positive evidence, you can already see it. Okay, negative evidence, if you say A, I think A is followed by B. Okay, this time I see A, then I see B, that's clearly positive evidence for this correlation. Negative correlation comes when you see A, but it's not followed by B. But it's a tricky here that you're not going to see something which does not happen, right? You see what happened, you don't see what will not happen. So where are the negative evidence come from? This actually is a big question in general in cognitive science. Okay, there is a big debate about, for example, in language learning, about where the negative evidence come from, right? According to this theory, in a lot of situations, negative evidence come from failed anticipation. So you don't see a negative input. There is no such a thing as a negative input. You expect a B, which didn't happen. And so you interpret that as a piece of negative evidence, but for all A is always followed by B. Okay. So you need to have this anticipation to realize that B does not happen. If you don't even have the anticipation in the first place, okay, you only see D, F, K, but you don't see, oh, there's no B. It will never occur to you in the first place. Okay, so that's one tricky processing that handled by this buffer, because here we explicitly handle relatively simple temporal information, and which is relatively easy to be handled at the front end, rather than wait until everything go into memory. And in that place, in principle, you can still do the kind of reasoning, but it will be much, much more complicated. Okay. So that's a major change. Now, again, we are not going to have the time to go into all details, but you will see this is kind of like the current form. It's still relatively simple, especially if you compare this picture with, if you Google, say, cognitive architecture, okay, you have hundreds of them, which are usually much more complicated than this. Especially, they typically consist of functional modules. Each of them carry out a certain cognitive function. And the philosophy of NARS, I have explained several times, is use the unified approach. You don't see functional modules in terms of cognitive function. But unless you say, oh, inference and memory is two separate functions, of course, we still have that. But it's kind of like to the minimum. So now let's see, given that picture, what is the experience of this system? This is important because actually I start to talk about the experience from day one, say that everything NARS does is based on its experience. The goal is to adapt to its experience, blah, 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 blah. But what exactly is experience? In the previous picture is relatively simple. It's just a sequence of NARC's input sentence. And that's the experience of this. Now, in the new architecture, we have several types of experience. The first type is what I mentioned. That's kind of like what people tend to think about first. We can call it external sensory motor device. The most typical example is a robot or some kind of sensor or actuator. Okay. It's directly related, connected to NARS and provide input to the system and also execute operations as a form of output, which will directly work on the environment. Okay. And one thing that makes NARS design special, this is something also I mentioned last week, is we do assume there is interaction with the outside world. But in the design, we do not assume any special type of sensor and actuator. Especially, we do not assume the sensor and actuator will be similar to that of a human being. We do not assume that. Even though there are tons of practical purposes to use them, of course, we want the vision to be similar to a human eye. But that is a possibility, that's not a necessity. Instead, we design this kind of general purpose channel interface so as you can build a device-specific channel, and that also allow the system to add new channel in the future. Say, if you say, okay, I want the system to use vision using some kind of light sensor, well, you just build a channel for that. And this channel will do what now you see. It contains a buffer which will do information pre-processing, as well as it will convert the input signal into Narcisse format. Okay? And that's clearly depend on the concrete situation of the device, so that cannot be general purpose. And also for the output side, it will convert NARS operations into command that can be accepted by that device. So different device, clearly they accept different commands. So we do that kind of customized special purpose translation in the channel so that the system design itself can be independent to the concrete type of device. So that's what I talked about as a plug-in input-output device before. So that's kind of like the detail. So for example, we still want some level of generality. So for example, what Patrick recently did is to provide interface between NARS and the robot operating system, which is already general purpose software which can be used by different type of robots. So with that interface, we don't have to do this channel thing for each individual type of robot. Instead, we would just use this robot operating system. So again, there's a kind of detail, but that's the basic idea. Okay, that's how we handle device, physical device. And this, another thing is what I explained with some kind of detail last week. That is, we can also control internal sensory motor, which is about the self-feeding, self-awareness. The system need to collect information about what's going on within myself in terms of the reasoning process, the current status, the emotion status, and so on, and use that information to control its own activity. Okay, and so that kind of information is collected mostly from this new internal experience buffer, which will hold the information inside. You'll see that here, NAR's philosophy to treat external environment and internal environment is kind of like highly in parallel. The difference is the sensor and actuator. That's clearly different, but the principle remains the same. Okay, you collect the information, you organize them, you pre-process them, you selectively feed some of them into the next layer. Then what? And then now you can see that eventually, this is the place where all the information from different channel, from different modality are combined together. And also here, we are going to do some compounding. We are going to try to find some regularity. For example, wherever I'm seeing something, I'm hearing something at the same time. Say how to recognize a cat, right? The image and the sound are combined together, which will give you a better recognition than each of them by itself. So what else we are going to say more today is not only we have sensory motor. Well, yeah, since everything is start from sensory motor, but we usually have an important level of abstraction. That's what we call communication. Communication in this context is between two systems. So between two systems is different from between a system and its environment. Why? Because the other system using language to communicate instead of physical, say, light signal, sound signal. What's the difference? What makes language different? Even though at the front end, of course, language always also start from sensation of sound or pattern or whatever. The important thing about language is we built an abstract level of convention on top of the physical signal. Okay, the mapping between two are more or less arbitrary in the sense that it's formed in history. There is no deterministic relation in most of the situation. Why this sound corresponds to that meaning? Well, but as soon as you build that relation is there, and also it will be a convention maintained by everyone using that language more or less. So what it provides, it actually provides a way to directly communicate in the concept level instead of going through physical, chemical signals. Okay, so that's what we call a language. And here in this context, actually, we are talking about several different types of language. First, of course, is this special purpose language, Narcisse, which we introduced from the very beginning. So that's the special format you communicate with NARS. But in this new channel, in this new design, we add two more types. One more type is what we call computer language. In a general sense, this in this picture corresponds to what we call a knowledge channel. Typical example is we can hook up NARS with an existing knowledge base. For example, we have tried, say, ConceptNet, if you know, heard about that, WordNet, all this kind of thing. Okay, so it's similar to how a human uses a reference book. If you need some knowledge, you don't have to remember all those things in your own mind. You can just check your reference book. In this case, NARS can send a query to a database or knowledge base and get the answer back. And here, in this case, this channel will basically do this translation between one specific language used in that channel and the Narcisse to and from between the two. So this is relatively simple, but it is very powerful, so that the system can use existing knowledge source. And this actually can be further extended into other computer software, right? You just call a software. For example, one thing we have been talking about is to use the mathematical functions built into, say, Java. There is a package, right? The math package, and in C also there are a whole bunch of functions to do all kinds of calculation. So whenever NARS need to do that kind of calculation, it doesn't have to do it by itself, even though in principle it should be able to do some of them. But then you just send a query. It's kind of like a remote function call, right? Technically speaking, there's nothing magic. As a metaphor for us, it's kind of like we use a pocket calculator for complicated calculation. We just, instead of trying to use our mind, we just type in the calculator, we get a result back. Okay, so you'll see in this way, actually a future possible usage of NARS is some kind of intelligent operating system. Okay. Any hardware, software, so the hardware can be hooked to it, kind of like as a sensor and actuator. The software can be hooked up as kind of some kind of knowledge source or software tool, okay, which is driven by command and will give you the result back. So it's kind of like your toolbox. So another thing, of course, very important is human language, which is much more complicated because you don't have a fixed set of rules to do this translation, which we will say a little bit more later. And also, human language is not completely handled in channel. It's much more complicated. It's a combination of the channel processing as well as the main memory and the inference engine and so on all work together. But anyway, now you can see the system's experience can be very rich. Okay, in a sense, it's comparable to that of a human being, even though, of course, it will not be identical to a human being because it will have different sensors, it will have different knowledge sources as we usually have access with, and so on. Not to mention is hardware speed and the memory space. It's not something like us. So we're not going to go into detail, but we are going to talk about some general principle here. And also, by the way, today's talk is also different from the previous weeks in one important way. In the previous weeks, I almost always talking about something we have already implemented. Okay. Today's lecture, part of them is already implemented. Part of them is the part we have a detailed plan, but we don't have all the code yet. And also at the end, there are some of them we only have a very high level plan, but we are going to talk about them just to show you a complete picture of this system, at least in our current mind. Okay. So language is this part. We have already done some natural language processing experiments, but we haven't really, you cannot just talk with NARS using a human language yet. Okay, you probably have already found that out, but we do have a plan. So before we go into that, let's first see what language means in this context. Very roughly speaking, for this type of system, when we are talking about a language, very often we're talking about two separate things. And very often people get them confused, which is really bad. Okay. One sense is we're talking about language used for knowledge representation. That is, within the system, all the knowledge are described typically as a sentence of a certain language. In the NARS situation, of course, is Narcisse. That's the language used for this purpose. Another usage is communication. And Narcisse, you see, can also be used for communication, but these two usages are still slightly different, which we are not going to go into the detail. But the other language, like human language, computer language, blah, 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 is basically used for communication only. Okay, they will not be directly used to represent knowledge within the system. So keep this in mind, and this difference is important. Okay. There are some people who argue it's the best way to keep knowledge within the system is to directly use human language. There are all kinds of trouble with that approach. We don't do it that way. Okay? But I'm not going to discuss that in detail. But we do use that for communication because it's more convenient for human beings. So don't confuse these two. Now let's see. Okay, with this new architecture, what is the knowledge or the memory looks like, or how the knowledge are represented within? And this also I want to compare with the previous picture I showed you, this one, again, that several weeks ago. I hope you still remember at that time it's relatively simple, right? It just you have a directed graph, weighted. Every node is a concept named by a term, and every link is an inheritance relation, which can be either an active one, like a task, or a passive one, which is what we call a belief. Okay, it's kind of like this. The memory is just a huge network like that. And now you see that we basically have the same thing. It just gets more complicated. It's still a conceptual network. But now you see that we begin to have several types of terms or nodes. Some of them still looks like before. We are using English words as a name, but the meaning is already very different. Okay. Previously, we used the English words actually to mean the concept correspond to that word. Okay. And in this one, we literally talking about those words in English themselves. So this is, we can call it the linguistic terms that correspond to the concept. Each of them correspond to a word. Of course, also phrase, even sentence of a certain language. Of course, it doesn't have to be English and also have some Chinese involved. Okay. So what we have before really only represent pure concept is this group. You see that I deliberately pick something that doesn't make any sense. It's just an internal ID. Okay, So for example, this one, as you can guess, this T135 actually intuitively corresponds to the concept of bird, if we talk about it in English. Okay, so this one forms relationship with other concepts as well as with their natural language representation. Here we use this green symmetric relationship, meaning that to a certain extent, this word can be used as a symbol of that concept. And the concept is used for internal processing, and this word is mostly used for external communication. And there is a mapping between the two, but be careful, this is not a one-to-one mapping. It's typically a many-to-many mapping. So, which means the same word can be used for different concepts, and the same concept may correspond to more than one word, and they're all familiar with that phenomenon, no matter in which language. Okay. So we have that, and also what's new, we have sensory input, okay, which may start from a picture or movie, and also it also goes through multiple levels of abstraction. Okay, like that this image is something like an abstraction of several concrete photos, and which will be taken as a general concept. You'll see that one key difference, okay, all of those things are called concept in ours. So in ours, the concept of concept is much broader, especially compared to traditional symbolic AI. Okay, in that system, they typically correspond to a concept to a word in human language. Well, in ours, yeah, it can be the case, but it doesn't have to be the case. Okay, so everything, as far as you have an internal ID, well, from a computer scientist point of view, this is trivial, right? Whatever you have, you can have an internal ID to name it, then that's a term, and the single name can be taken as a concept. This is not just a semantic decision or naming. We can actually do reasoning on those terms or on those concepts, just like everything else. Okay, we can do reasoning on this because we have extensions which are more special case. We have intentions, you'll see eventually is abstracted to be connected to an internal concept. So in this way, we don't have a sharp separation in traditional AI, you know, what is symbolic level, what is sub-symbolic level. Well, that distinction is still here, but it's a matter of degree. Okay, instead the relationship is continuous. And also you'll see on this side, we also have something, I don't know how to draw them, which is related to internal feeling as well as to operations. We have already said that some of the terms have a procedure interpretation. So whenever you mention that term, you are actually talking about an action the system can take. But you can also reason about it in the same way as you can reason about the others. Have a question there?
Yeah. Can we say that for example, the picture on the bottom, the orange bird is also an instance of that abstract, but on the same time in our concept?
The same category, okay? So this one is in extension of this one. And this one is in extension of this one, and so on. And the inference rules, all the same. I can do induction among image, no problem, because you think about it. In ours, all the reasoning I mentioned before is you can use one as the other based on their similarity. Okay, I can use this as this in certain contexts to a certain degree. I can use this as this or the other way around. So that's where the unified treatment comes from. Okay, given this, what we call concept-centered knowledge representation. And concept is nothing but part of your experience. Some of the experience can be verbal experience, some of them can be sensory, some of them is your internal feeling. So what? The content are different, but the rule to handle them is basically the same. Okay, adaptation means what? Means you use your past experience to predict about the future and to decide what to do. And it doesn't really matter whether this is talking about verbal experience or visual experience or internal feeling. Okay. So that's a key observation we made in this research. And also there are some compounds which is hard to draw, but the basic idea is I can build a structure with several of them. I use this structure. Well, I can just simply give the structure a name, right? And after that, this whole thing will be used just as a single piece. The same trick is like in programming, right? You start from instructions, statements, and you build the functions, then you build function. That's how you handle complicated situation, right? So the same story here. So we can build a hierarchical concept structure to represent the system's experience in a summarized and organized manner and combine different types altogether. Okay, so this diagram, even though it's simple, I hope you can remember that's actually what makes the system, make ours very different from many other things. It's not symbolic AI, it's not a neural network, even though I have similarity with both of them here. And not to mention, we also have truth values. So each link is drawn to a certain degree. And also we have priority values. So whenever you use one, you don't connect it, you don't take all of its connections into consideration. You pick some of them, blah, 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 blah. Right? We have talked about that before. So what is our plan for natural language processing? Again, this is the early stage, but we can still say something which show the difference between our approach and everyone else. I think the number one thing is a common sense, but typically ignored. That is, we treat language not as something by itself. We treat it as a tool for communication. As I mentioned before, and in this context, we are talking about communication language, and the whole purpose of language use is to communicate with other systems. What does that mean? First, I will show you this list. That means our processing order is exactly the opposite with the common convention. What's the common convention? You start with syntax, right? You have an input, you do parsing. You recognize the type of word, right? And this is a noun, this is a verb, and so on, and you have a grammar. That's a Chomsky tradition, symbolic tradition, okay? And you build a parse tree. So that's the first step, and you ignore the meaning completely. The second step, you do semantics by mapping each of the individual words into your internal representation, you call it a concept or whatever. And finally, you think about pragmatics, that is what you want to use this information for, to answer questions, to drive a robot, and so on. But according to our opinion, it should be the other way around. The primary function of language is as a tool, you want another system to do something for you. So it's kind of like an operation. This is related to the concept of goal-driven communication, or in philosophy and linguistics, they have a research under the topic of speech acts. So whenever you say something, in many situations, you're doing something. Okay. In the AI context, very roughly speaking, you're using another system, well, here use doesn't have a negative sense, right? It just means, oh, we cooperate, or you help me in three major ways. One is you use another one as your sensor to get information you don't have. Second, the other way around, as an actuator to do things that you cannot, or for some reason you don't want to directly do. Okay, you ask someone to close that door, to bring me a cup of coffee or something like that. And the third one is in between. You'll use another one as an information processor. And you'll see all these three functions put together, that's your own functionality. And you use other people to help you wherever, for some reason, you cannot handle. For me, that's the basic function of language. This is different from some other opinion which say, oh, language means share information and other people give you part of description about the world, and so that you can fill in that with yours to make it more complete. That's yeah, sometimes that's the case. I don't think that's accurate. Okay? The more accurate way or more comprehensive way is you're using other people to do things that you cannot do by yourself. Using language as the channel or media to carry over this request and also to receive the result. Okay, so because of that, actually, all the communication activity in Earth are goal-driven, and that's carry out a task, just like all the other tasks. As I said, okay, when you want to close the door, you can just walk over and you can close it yourself. But under certain situation, you cannot do that, and you have a reason to ask someone to help you, which is more meaningful or more practical in that situation. That's kind of like a replacement of your own action, right? And then you make the decision that in that situation you want rather do that rather than do compared to do it yourself. And also, not to mention that in many other situations, you simply cannot do it. You have to ask. Okay. But that's the difference. But the similarity is, you see that in this context, you send out a request is basically the same as you decide to take action yourself. The decision making process are more or less the same. This is just communication give you another option to achieve your goal. Okay, so that's a very different attitude. For example, when we process natural language, if you take this point of view, what a sentence or a word means to you primarily is the consequence. Okay, if you know whenever you say you make a certain type of sound, it will always cause something to happen. That's the meaning of that sentence. That's the primary meaning of that sentence. This is clearly true for babies when they start to learn language, right? They don't really understand every word. They just say, oh, if I say this and that kind of thing will magically happen, then whenever I want that to happen, I will do that. And this is still true for us. This is typically the situation wherever you see language phenomena like proverb and idiom and so on. The meaning is in the whole sentence. It's not in the individual words. Of course, the individual words matters, but gradually this whole sentence is the basic unit of meaning. So we probably is going to start to teach the system in this way. And it will know a certain sentence means certain things to other people. Then what? Then of course they can only handle very simple situation, right? More complicated situation, you need to go into that sentence to recognize the individual meaning of the words and phrase in it. In another context, it means nothing but we have seen in the previous slide is this kind of relation. Which word corresponds to which concept? And you see why this is important, because your concept in this case, this kind of concept are internal, only known to yourself. Okay, if you want to communicate with someone else, you need to use a word which is part of language, which is shared by a whole community using that language. Even though, yeah, we do have a misunderstanding because this word map, into this concept in you, but it map into a different concept in another person. That's quite common, but to a large degree, we still have something in common. So that's what makes communication possible. Okay. So that's the semantic part. So you can use this to build new sentence you never heard before, but you know the individual words meaning, and you know that's finally where syntax gets into the picture. You want to build a compound using the known components in a known structure, but the compound itself may be normal. Okay, here you do need grammar, but that's more for more complicated stuff. Okay. So you'll see that if you do it in this way, it's kind of like exactly opposite to the traditional Chomsky tradition of language processing. And also you can compare it with the current popular deep learning approach. You can also clearly see the difference. Okay, deep learning take end-to-end training approach typically, so they don't really even bother to distinguish these three layers. Okay, so what do you get? What you get is a probability distribution about the association of words, which is good for many things. But if you really go into detail, and people say, oh, it doesn't really understand what it's talking about. Okay. Yeah, I'm not saying it's bad. I would say that that's not good enough for our purpose. Okay. For example, pragmatic. The language, the primary reason, for example, in this conversation, what I'm doing here, I try to change your mind. I'm not trying very hard to convince you I can speak English. But of course, I do need to take that into consideration. I need to try my best to use the correct English, otherwise you will get confused. But that's not the same as think about all the big language models, say GPT-3 and so on, what they're doing. They're speaking like a typical English speaker. And I'm not speaking like a typical English speaker in terms of the content I'm going to talk about. Okay, actually, I show you in every week, I'm showing you something which is opposite or very different to the opinion of the majority of the researchers in the field. If I'm trained to use a language model, I should say what most people agree with. Right? That's where the statistics tell me. But that completely failed my purpose. I don't want to say something which is predictable from a statistical point of view. And also, you don't want to listen to that. So you see, the difference actually is not in the technical detail. It's in a more philosophical level, what language is for. Okay. So, but yeah, that sounds fancy. How to do it? Well, nothing special by reasoning. You see, every word is a concept, right? From the learning process, we're going to gradually learn the relationship between a word and other words, where statistical pattern is still useful, right? This one is always followed by that one. If you don't do it that way, it sounds weird. Well, that information is still there. But also we have this relationship between word and concept explicitly. And also we have the relationship between word and usage and its consequence when you're using it in a special context. Okay, that thing is not, at least not explicitly recognized or processed in many other natural language processing technology. Okay. Yeah, everyone say, yes, we know we're not there yet. We are still improving our technique. Well, yeah, that's true for everybody. But there is still a difference about the direction you are moving, whether you're moving in this direction at all. Now, I already covered this topic. What is understanding? And I have claimed, deep learning doesn't really understand. How do you know whether your nerves really understand? How can you claim you can understand, or what understanding is about? Well, at least we can talk about my opinion about that. To nerves to understand a sentence basically means to process it as a task, just like all the other tasks. But still, what do I mean? I mean several things. First, say an English sentence or Chinese sentence feed into the system, it will gradually convert it into narcissism, just like everything else. But how? You see, I have already gave you the basic idea. The system will first try to see whether this whole sentence as a unit corresponds to some existing concept. Okay? If that's the case, the system doesn't even bother to analyze this sentence further. We'll just take this as a whole. Okay, I know what I mean in normal situation. Okay. Well, yeah, I can be wrong, but that's also how we typically handle it. If this whole thing doesn't correspond to a concept, then I begin to cut it into pieces. According to what? According to my grammar knowledge. And for each piece, I map that word and phrase again into an existing concept. If not, I will continue to do this as a recursive process until it's done, or until I run into something I never heard about before. Well, even in that case, I can still create a new concept correspond to that new word. I will try to figure out the meaning according to its relationship with the other part of that experience. Okay. And I believe that's how we learn language in at least one part of that process. And also, that's this part. And of course, I will add it into memory selectively. Another piece also is important, and the process doesn't stop there. I begin to do forward processing. What I mean, I take that piece, after I turn it into narcissism as a task, I combine it with my existing belief to see what I can derive. That give me what? Give me the implied meaning. That is a key component of understanding. Okay, very often when we say, do you understand me? We are not talking about the literal meaning of a sentence. Okay, I mean what I mean. If I say I feel cold, I'm not really talking about temperature of the room. Yes, I am, but that's not what I mean. What I mean is maybe someone know how to turn up the temperature, right? Or close the window. And that's not in that sentence, but that's what everyone can get in normal situation. How to get that kind of thing? To do forward reasoning in this case, first, again, we start from pragmatics. We kind of like think about why he mentioned that. That usually means that he thinks that's an issue, right? Or he doesn't feel like that, and he suggests it should be changed somehow. And do I know how to change it? If I know, I probably should change it, and that's understanding. But clearly, if I put it in this way, that's become very obvious. The result of this kind of understanding does not only depend on the input, it also depends on your knowledge about that person, about the scenario, about this context, and so on. That means the same sentence will be understood in different way by different people. That's a normal situation. There is no such a thing as what is the true meaning of a sentence. Okay, I bet that applies to today. Okay, my lecture will be understood by you differently, which is normal. But of course, there will be something in common, right? Since as far as you're listening to me rather than completely thinking about your own idea. So this will point to a very different direction about understanding. Instead of trying to achieve a true, correct, accurate understanding, we're talking about how to handle this input and how to combine it with my knowledge to get something useful to me, and also hopefully not too far away from the intention of the speaker, and so on. Okay, and you see, I hope at least you can understand the difference of this approach and the other approach, which you typically find in textbooks about natural language understanding. So now we can move a little bit higher beyond these details. Now we can see that given everything I have said so far, how the behavior of a concrete NARS system are determined, which is again very different from everything else out there. I would say it's determined, roughly speaking, by 3 factors. The first, of course, is the design of the system. This is what we have been talking about so far in all the lectures, right? And you have grammar rules, inference rules, memory structure, attention mechanism, and so on, how NARS runs. And that will decide its behavior to a large degree. But a second factor is what I call configuration. You can call it different thing. It's kind of like, the first one is kind of like the mind as an abstract model. The second one is we're talking about the body. You put this mind in. And this will lead to some ambiguity in our terminology. You see, whenever I'm talking about NARS, most of the time I'm talking about the abstract, formalized model. Sometimes also I'm talking about a concrete implementation of that system. To clearly separate it later in some of my publications, I call this a NARS plus, okay? NARS plus, it just means this mechanism implemented in a concrete body. What's the difference there? First, hardware. Here we're talking about memory, processors, and so on. You see that even if using exactly the same software, when you put it into different hardware, of course the performance will be different, right? A very fast supercomputer and a very slow laptop, clearly the result will be different. The system's capability, what kind of problem it can solve, and how fast we can solve them will be very different. Okay? And also not to mention, I have already mentioned a sensory motor, like what kind of sensor you gave it, what kind of actuator you gave it. The same NARS can be implemented, I mentioned before, in very different, say, robots. Okay? It can be a 2-leg, it can be 4 wheels, it can use it can be even flying. And then the behaviors will be completely different, even though the mind is basically the same. Okay, because it just plug in different with different channels, control different actuators, but the logic, you see all the inference rules and the control mechanism, but how to resource distribute it in principle, they're all the same. What else? Parameters. This is also interesting. Okay, we haven't spent too much time on it, but in many places within NARS design, there's some value or some design decision which has no optimum choice. To take something which is relatively easy to understand, memory usage. We assume finite processing power, which I mentioned in the first thing, right? Say, if you gave this NARS implementation or NARS plus the same amount of memory, which is already fixed, but there's still an issue. How do you divide it for different units which use memory? For example, main memory, and each of the buffer has a special memory in it. All of them influence the performance of the system, even though the total is the same. Okay, so for example, if you gave the vision channel a larger buffer, the audio channel a relatively smaller buffer, the system's visual ability will be stronger compared to the audio ability, compared to the other way around, a relatively small vision buffer and a larger audio buffer. What is the optimum solution? There is no such a thing. If we talk about the robots, and that actually depend on the working environment, the task you gave it, and many other factors, right? So different configuration will work better for different scenario. What if you don't know the scenario in advance? That's our basic assumption also, right? You don't know what kind of scenario you are going to run. Then what? The different configuration will give you different system. They're all intelligent, but with different personality. Just like different people have different personality. Very often, it's really hard to say which one is better, even though that question itself sounds, politically incorrect, right? Most people will say, there's no such a thing. So, but when you design an AGI system, if there are multiple choice, what kind of personality you're going to give it? Okay, and our current understanding is, well, there is a range of kind of like a normal situation, right? You don't be too extreme, like to put, for example, everything into one channel, very little to the other, which will give something very weird. But still, you cannot say that's wrong. Okay, you can have a more balanced one, but maybe not interesting enough compared to the more extreme one where you're exploring special tasks. Anyway, that will give you a lot of individual difference or diversity among your implementation. This reminds me something like when you see some Hollywood movie, okay, they show a whole bunch of robots which moves exactly the same way. They just show you they're stupid, okay? And if it's a truly intelligent group, each of them should be different. Or there is reason to do it that way, rather than to use the same parameter again and again among all of your individuals. Okay. And also, memory content. Our previous assumption is not just an assumption, that's what we have been doing, okay, in practice, is the memory initially is completely empty. Just like this type of network, initially, there is nothing. So the first input sentence will build two nodes with a link in between. The second one will add more and more and more, and the reasoning process will also change that. You can see, if you see this kind of a picture, you will see how this network roughly grow over time. But Of course, we have the ability, if you really want to train a complicated memory structure, you cannot do it within, say, 8 hours in a working day. You do what? You save the current memory content somewhere into a file or a database, whatever, and you go home, okay? And tomorrow you restart your system, you load it back, you continue to use it to run. From the system's own point of view, if we really have a consciousness or self-awareness of the system itself is continuously running. Okay, this pause in between is invisible to the system because the memory is perfectly maintained and reloaded into the system. But that also increases a very interesting result. That is, if I train a system to a certain state, I save that memory, and the next day, and not only I load it back, I make 100 copies. I put them into new NARS class. And for that 100, they were born with a memory. That's what we call preloaded task and knowledge. Okay? It's kind of like innate to them because that's not from their individual experience, but that's from someone else's experience. Okay? So it's kind of like you're copying someone's mind and start from there to live your life. But starting from that point, that's 100 copy normally will become different, even though they start from the same initial memory content. Why? They will have different experience. That experience will change, will shape their memory. It will also change what they built into them initially. So all these three things put together will decide the behavior of NARS when you're giving it a task. What's the important thing? The important thing is to remember, unlike traditional system, computational system, the system is not completely determined by its design. Which, if we talk about this 20 years ago, which sounds like a surprise. Now we already know, oh yeah, of course, machine learning, right? There is a training process which will form its behavior pattern instead of designing it into it, okay? But that's still different from what we have here. Because typical machine learning system, after it's learned, it becomes fixed, or it converts to a fixed status. After that, you can only make minor change. In NARS, on the other hand, actually most of the stuff come from the experience of the system, not designed into it. There are several very important theoretical implications of this. First, you see the title of this slide. Everyone knows it, right? For human beings, their behavior is determined by nature and nurture, and also, of course, there is no clear separation. There is a complicated interaction between the two, but roughly speaking, we can still talk about nature and nurture, which makes sense. So in NARS, what I mean, and this is clearly the nature part. Okay? This is not the system's own choice. This does not depend on the system's implementation and experience. That's something we built into it. And also, when we talk about learning, I mentioned this part cannot be changed by the system at all. And finally, this experience part is basically what we call nurture, just like humans, okay? The knowledge, most of the knowledge come in that way. The interesting part is the part in between. I will say that we don't have such a thing. for human beings, roughly speaking. Okay, this is kind of like, yeah, the same mind put into different body, and also you can preload things into a mind, which will of course cause some problem, but also bring special advantage for artificial intelligence, which is not there in natural or human intelligence. You cannot educate a student and then make 100 copies, right? But you can do that with AI. Very simple. Everyone understands that. So that raises another theoretical issue. That is, just to do everything like a human is not always the best choice. Because you're implementing intelligence in a computer system, you are supposed to use the advantage of a computer system, while keeping the same principle as intelligence, which you observed from human intelligence. Okay, so to me, an important topic, which I'm going to talk more, I guess, next week, is what to learn and what not to learn from human intelligence. If you learn too little, you're not intelligent. If you learn too much, you're duplicating human intelligence. That's actually not a good idea to me. And this is just one example to show that. Another thing we can discuss is, where is the intelligence? Again, that's a topic I have very different opinion compared to many other people. In this field, very often intelligence is equivalent to problem-solving capability. And that's actually from psychology. But I'm not blaming the psychologists, okay? They have reason to do that, to take that position. Because in human mind, intelligence and probability, problem-solving capability are highly correlated. But that's not true in computers. Why the difference? Because a human baby doesn't grow, it's born with a whole bunch of problem-solving capability, so that capability basically comes from learn. If you are capable, it means you learn faster than the others. In computer, you don't have such a correlation. You can build in a whole bunch of stuff into a computer, which make it very powerful by design, even though it doesn't learn anything. Okay, so according to my definition, actually intelligence is basically here. It's in design. On the other hand, problem-solving capability mostly come from configuration and experience. Of course, design also matters a lot. But there is a key difference. So I also, according to my opinion, which is a little bit controversial, the intelligence of the system remains mostly constant in its way. Even though its problem-solving capability, of course, grows over time. We don't want to confuse the two. I think a lot of problem in the current AI research is to confuse the two. And instead of focus on intelligence, they're focusing too much on concrete problem-solving capability, which is useful, of course, but it's a different story. Now, beside design, what we can say about experience? Well, that leads to the concept of education. What is education? In this context, you're controlling this system's early experience. Okay, after you build it, no matter whether with a preloaded memory or it's completely empty, let's take, say, the completely blank memory case, that's more typical. How do you load the thing into it? I already said in this case, right, each piece of knowledge you put in will create some nodes and links, and gradually you will build it. Yeah. Does it matter how you put things in? Even though the content remains the same? Even according to our common sense, everyone knows. No, that's not the case. This is not like you load the data into a database. Okay? What matters, if you want to use this education to gradually build the content of the memory, which include the desired beliefs, skills, priorities, and concepts, you need to control what information to give it, in what order, and the timing. And you can control that in several different ways. You can use something which we call tutoring. Is kind of like you're sitting in front of the console of the system and typing and or even talking with it, and give it information and test its understanding or construction of its internal memory, and provide feedback for its behavior, some kind of reward and punishment. Okay, and also you can put it into a reading mode, which we currently already have. Instead of typing in sentence by sentence in the user interface, we can ask NARS to read a file, which is a compiled sequence of Narcisse sentence. So it will read it one time, one line at a time, just as if you're typing it in as a user input. Okay, technically there's nothing different. But this, of course, is a much more efficient way of testing the system. And also it will guarantee accurate repeatability when you're doing debugging, right? So that's something we use a lot, which is already there. But for that mode, clearly the order of the input matters. Just like humans, you want to start with something relatively simple, then you produce something more complicated because it can build on the simple stuff gradually, create its own concept structure and so on. Okay. And order matters. You don't want to jump from one topic to another, just like that will confuse everyone, right? For the same reason, it will confuse the AGI. You probably want to cover one topic for a while, then you switch, do a physics class, then after an hour, you do a chemistry class, rather than, intervene, that's two fields, one sentence from here, another sentence from there. That's clearly not a good way to do things. And the same thing is true for NARS. If you think about how it processes information, you will see that's the case. Okay? And also you can ask it to explore things by itself, especially if we're talking about a robot. We assign some task, then we do some reward and punishment and so on. But probably in the future, it will be a combination of them. And you will see a lot of similarity. This is how you educate a human child. But also as well as with a lot of difference. So yeah, it's my prediction that the education of AGI in the future will become a field all by itself. It's not completely determined by the design. And after education, what if, you graduate from that school, or not you, a nurse? Unlike machine learning, you don't say it's already learned and now switch into working mode. Instead, this thing continues, but in a less restricted way, less planned way compared to education. Okay? Education is kind of like the society force you to sit there and get this experience to a certain degree. But then you become an adult, you graduate, you interact with other people. But in that process, the same thing happens in a slightly different way. Okay? Your opinion will still be influenced by the people you communicate with clearly. And you also get social knowledge, which include knowledge about how to deal with other people. What kind of expectation you can have about other people's behavior. And also you want to fit into other people's expectation about you so that you can be predictably communicated or cooperated with. And you don't want to be completely different from other people, even though that sounds cool, right? And then people don't know how to do, how to work with you. It's just, they have no way to establish reliable expectation. Okay. So it's a balance. And here also, there are two different contexts. One is computer and human. One is between computers. Think about what if we have a whole bunch of NARs and communicating with each other. They are going to also form anticipation about each other, and they're going to talk about how can we cooperate to solve something that each individual cannot. Okay. So there will be a lot of things established. Another thing that related to this is what we call subjective belief, which is only completely based on your own experience, will gradually, to a certain degree, grow into what we call objective knowledge. By sharing other people's experience, by taking other people's point of view into consideration. But still, the subjective nature is always there, is primary. The objective part is built on top of that, is a secondary, even though very often it's, of course, it's important. So this clearly is a big topic all by itself that I just want to briefly mention to show you that it is in our consideration, is in our picture. One more step, I already mentioned. If we're talking about a group of NARs, when I talk about socialization, I'm still standing on the position of one NARS, talk about its relationship with everyone else around here. Now, if we zoom out, we are talking about this whole group of NARS without focusing on any individual. What we can say. Let's assume it has a shared design, just the number one item I mentioned before, identical, but a different configuration, different experience. Then what? Then, in a sense, just like us. They will form different opinion, but there will be some overlap, especially if they talk with each other. Okay? They will have different skill. They can solve different problems. They will have different goal, even though the initial goal I gave all of them are the same, because their derived goals will be shaped by their individual experience. Okay. So they are going to have disagreement about how to do certain things, like how to keep the world peaceful, right? Even if they all want that. So the group as a whole can also be taken as an intelligent system, rather than just as a group of intelligence. Okay. This opinion also have been discussed by many researchers, especially in the context, ants and bees and so on, some other animals. Each of them is stupid, but this group altogether seems to be quite smart, can do something very complicated. Okay. And in our scenario, each NARS is already intelligent. But this group can be more intelligent than the individual, but can also be the other way around. Okay, it can be quite stupid and cannot achieve anything just because they keep fighting each other and so on. That's understandable. Just think about humans. Right? So, but anyway, this will give us a very interesting testing bed for all kinds of sociology theory or something like that. And also we can try to somehow get this group to do something that an individual cannot, right? I think the basic principle will be the same as how to organize a human group, even though the details will be quite different. What kind of social structure is the best? Okay. And decision-making process. And what makes a group different from one individual, even though the inference rules and control mechanism, blah, 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 are all the same. You see clearly the goal, belief, and skill, and so on of the group is related to that of the individual, but not the same. They're not the same. So that's the topic we can further study. And finally, now we say with this setting, we can discuss adaptation in a more general sense. We can actually distinguish several types of or forms of adaptation. What we have discussed so far, except today, the last 10 minutes, we're talking about the individual level, how to adapt to the environment based on its own experience. That's what we call intelligence to me. But also, we can move to the group level, assume we have a group of those individuals, where the form of intelligence or adaptation take a slightly different form compared to an individual. For example, one major difference between one individual and a group is a group have higher tolerance to internal difference, diversity, and so on. Okay? An individual, you can have different opinion in your mind. Of course we do, but it cannot be too much. Otherwise it will drive you crazy. Okay? For a group, there is a much higher tolerance, which is both a good thing and a bad thing compared to an individual. Okay? For some tasks, that works better. For some other tasks, it will just mess up everything. We all know that. But that's a form of adaptation, which is related to the individual, but not the same thing, which is commonly called collective intelligence or group intelligence. And finally, we can even move to the level of species. That is, not only we have a group. In this group, we keep have new system born and old system die. And the new system born have their configurations obtained through something similar to an evolutionary process, which means that with some change, not directly based on the individual or the species or the group's past experience. Kind of like random mutation, even though it doesn't have to be random, it just needs to be determined by factors beyond the experience of the systems. It's not like you're going to have a new way because it works in the past or you think it will work. The new way just come, then you try it, either successful, you'll survive, otherwise you will simply die, okay? Something like that. That's what we call evolution. Okay. To me, these three are related, but they're not the same thing. And especially, to me, intelligence and evolution are very different. In AI history, some people take evolution as a way of learning. Well, in a sense, it's true, but the internal mechanisms are very, very different. To me, it's kind of like a complement to each other. So evolution is good for things that you cannot learn by intelligence from your experience, not either from your individual experience or a group experience. Try something. Sounds crazy, which may turn out to work, okay, but you pay a price. The risk is much higher, and the time it takes is much longer than you learn from your experience. But that's a whole course all by itself. Okay, so I only want to mention it in a few sentences. Yeah, that's all. And this part, we don't really have all the code, but I do have some writing related to the topic I mentioned today. So if any of you are interested, and also especially our approach to natural language, even though it may sound novel to some of you, it's not completely new. Okay, in the linguistic field, if you check cognitive linguistics, many people have already argued for similar opinion, but they haven't get much attention from the AI community. AI community traditionally is dominated by Chomsky approach, and now statistics. I think we need something new, especially when we're talking about language. Okay, that's all for today. And yeah, today I'm roughly on time. So we can take a 10 minutes break and we can come back to do some discussion.